Okay, thank you for the introduction, and thank you to the audience to stick until the very last talk of the day. I would like to change gear now and talk a little bit about our effort. Sorry, this is okay. Our effort at UCSF towards preclinical in vivo imaging of actinium-225 with collimatorless detectors. So first of all, let me motivate why in vivo preclinical imaging of actinium-225. You might be familiar already with this, and the bottom line is that actinium-225 has shown excellent results treating solid and liquid tumors, as it can be seen, just illustrated on this study, where a single patient shows full remission after the injection with an actinium-225 radiopharmaceutical. These are from gallium PET images. Also, actinium is a gamma and an X-ray emitter, so it opens the possibility of alpha theranostics. One of the issues is that there are many different gamma rays and X-rays being emitted, as opposed to the usual technetium for SPECT. Also, the energies of the main gamma rays are much larger than this. But the main challenge is that typical preclinical activities are 100-fold lower than those with technetium, with the usual radio tracer for SPECT. So this is definitely a challenge for SPECT. And why do we want to image it preclinically? Well, daughters of actinium can detach from the radiopharmaceutical. And let me just illustrate this with this animation. So take actinium, which is bonded to this radiopharmaceutical, and it emits a therapeutic alpha. The issue here is that actinium decays into daughters that are also alpha emitters, and there is no warranty that these daughters remain attached to the original radiopharmaceutical. So this effect, this mechanism, and other biokinetics of the radiopharmaceutical needs to be studied, and they are best studied in preclinical in vivo models. And this can be achieved through the gamma and X-ray emissions by SPECT imaging. So first of all, let me discuss a collimator-based approach. So this is actinium imaging with a CCT and a CCT detector and a tungsten collimator, to show you a little bit what I'm talking about and the limitations of this technique. So we assembled together a planar camera with CCT detectors and a tungsten collimator. So we use these custom designed by Ideas CCT detectors. We ordered 4 detector heads. We are currently only using one, and these are manufactured by Redland. They are 5 millimeters thickness, and just to highlight that's why CCT is because the stopping power is better than sodium iodine, which is the more typical one for SPECT, at least historically. And we assembled the camera with a tungsten collimator. Tungsten is more dense and has a higher stopping power than lead, so in principle it reaches higher energies. And it's actually being commercially used in state-of-the-art SPECT in these days. So with those ingredients, we assembled the first generation planar camera with only one detector head. So let's test it now. And to test it, we use this BioNTech fillable mouse phantom that you can feel. And in our case, we fill it with actinium. So there is no radiopharmaceutical here. This is a low activity of actinium, 5 microcuries total. With this, it's a constant concentration. So here, the percentages I'm showing is just because the volume. And we just set it on top of the collimator with the CCT detector and run the experiment. So this is what we see with X-rays. This is for an hour exposure of the 5 microcuries, and you can see that you distinguish between the tumor, at least by eye. This is just a xenogram. There is no reconstruction here. The liver and the brain. What happened with francium? Well, things get a little bit more blur because of the higher penetration of the gamma rays, and for bismuth, it gets very, very blur. I should also say that this detector is not really optimal for energies above 350, and these events here will be in the overflow bin here, so that's why it's a little bit noisier. But let's go to lower activities. So we did the same thing with 2.2 microcuries. I'm just gonna flip through the slides. And as you see the activity going down, the images get noisier and noisier, as one would expect. And this is already at the realm of the injected activities for in vivo experiments with mice. And you can see that, yeah, by eye you can distinguish a little bit by the tumor, the liver, and if you have some imagination, the brain here, but it's really not optimal, and let alone the francium and the bismuth. If the actinium keeps decaying, then it's really challenging with this. So that's why we turn back to collimators and try to answer the question of whether we can get rid of the collimator. And I would like to talk about collimator-less approaches from now on. And mainly I will talk 80% 90% of the time about proximity. So what is proximity? The proximity principle is based on the solid angle dependence of the gamma ray detection. So this is essentially is just the density of the detected light. And just to illustrate the principle, well, I should say that this is a concept that was used in this paper here 7 years ago for different radio tracers. Just to show you, to illustrate you the principle, we filled these spheres with actinium, and then we could, this is an overimposition of the optical image with the gamma ray image, and you can see that you can distinguish by eye the spheres, and even if you get them closer. And also something to highlight is that the energy spectrum is much cleaner because you don't have that scattering from the collimator. You don't, this is a reminder of what I showed earlier. It's really hard to distinguish here the different contributions, while here you can even see the different X-rays individually. This is with CCT. So you don't require here a collimator correction, scattering correction, right? So now, to a more complicated case, take that mouse phantom that I showed earlier, and at those activities that the collimator couldn't really see anything, we're gonna see what happened with collimatorless. We just deployed this mouse phantom on top of the detector without the collimator, and we could see by eye the difference between brain, the liver, and the tumor here. This is for X-rays and for only a 20 minutes exposure, again, of a very low activity. And this is for francium and bismuth, which they get a little bit more noisy because there's less events, and also because of this feature of the detector I told you about earlier for higher energies. So now, you might be wondering, what do I do with this? What information can we extract from these blurbs here? So our approach was implementing a likelihood fit in order to measure the organ activities. So for that, if you assume that you know the position and the shape of each organ, including the tumor, and you assume that the activity in each organ is uniform, then you can build these templates here. Basically, this would be for the brain. The ground truth for the brain gives you this image here. The ground truth for the liver gives you this image, and the tumor gives you this image. And this is simulation, by the way. Now, if you sum them all and reweight them by the activity of each organ, which is literally the only free parameter in this model, you will get these Monte Carlo result images that you can match to the data. And to do that, you construct a likelihood. So this is actually the minus log likelihood. And you can minimize that in order to extract the organ activities. So we did that. But first, actually, let me talk about how we build those templates. It's very important for this method to know your detector response and where you have the organs, right? So in order to do that, you can just use CT. So we ran a CT of the mouse organ, the mouse phantom, sorry. We segmented it using ITK Snap, which is an open, well, I don't know if it's open source, but it's a source. It's a tool that everyone can use, including the body. We included that as a voxelized digital phantom into our GM4 detector model. And just one more detail is that we modeled CCT. We also modeled the charge induction efficiency in CCT in order to make our model more realistic and to model that energy bias and also the efficiency. So now let's go back to our data and compare it to the Monte Carlo after the likelihood fit. So this is our data for X-rays. This is the Monte Carlo, and you can see that after the likelihood fit, it's very well matched. You can do the same thing with francium, which again is a little bit noisier for the data. We don't simulate the noise in Monte Carlo or any detector artifact. That's why it's cleaner, and for bismuth, it gets something like that. And let me say that this is for just 1 minute exposure of 350 nanocuries. So now into more quantitative results. What we did here was to calculate the bias. So how well can we actually measure the activity, right? We know the activity that we are putting in each organ, so that's the truth, and then we build this ratio by measuring the activity divided by the truth, and that's what I'm showing here as a function of the exposure for X-rays. And the bottom line here is that with only 10 seconds, it already starts somewhat plateauing into about 20% bias. And this bias is probably associated with the fact that our model is not perfect yet. We can do the same thing with francium and bismuth, and this would be the result. And the bottom line is that the bias is lower than 20% for only a 10 seconds exposure of X-ray, for a minute exposure of francium, and for a 5 minutes exposure if you want to look at bismuth. But now this is a somewhat simplistic case with just 3 volumes. We wanted to answer the question of what is the limitation of this technique, right? How far we can go. So in order to do that, we use a more realistic simulation in a more favorable case, in which we use now a top and a bottom and a top detector, so top-bottom configuration. We also took a CT scan of a real mouse. We segmented it, and we included it as a voxelite phantom in our model. And we also assume an ideal detector, meaning that we don't have noise or detector artifacts. Our background model is extracted from our real detector, and we also wanted to plug in some realistic activities in order to mimic in vivo conditions. And as opposed to the previous case, for instance, here you can see that the liver gets most of the activity just because of the volume and the weight of the liver. And this is the uncertainty that we get after we run this likelihood fit over 50 simulated data sets. So this is in order to evaluate the performance with pure simulation. X-rays, francium, and bismuth, and you can see that the uncertainty collapses or like converges as the exposure goes higher and higher. And just to summarize, the bottom line is that the uncertainty is smaller than 20% or about 20% for only a 10 nanocuries field organ in 1 minute for X-rays. That's 15 nanocuries in 5 minutes for francium, and 15 nanocuries in 20 minutes for bismuth. So we are also doing the same thing now in the most complicated case, which is in vivo. So I'm just going to show you the images because we're still quantifying them. And this is for a radiopharmaceutical that is being developed at UCSF. So this is actinium-225. And this is for X-ray, for francium, and for bismuth. And the question that we want to ask is definitely what is the uptake in each organ. And to do that, we'll apply the technique that I just showed, and this is just very preliminary, so I don't have more results on this. So let me turn into Compton imaging now. You might be more familiar with Compton imaging, which is as a collimatorless approach. And we are trying to investigate onto the near-field Compton imaging of low-activity sources. I bet that you are familiar with the Compton imaging principle, so I won't touch on that. But I will just say that in collaboration with Lawrence Berkeley National Lab, we started collecting data with this commercial camera from H3D with a low-activity barium source. We're just using the 350 keV line, and for a 10 minutes exposure, we could pinpoint the source position. This is in the 2D space. This is, again, very preliminary. Just ran this analysis last month. We are going forward with this analysis and characterizing this approach. And why? Well, the ultimate idea is that we would like to have a Compton and proximity camera concept unified together by assembling this Compton camera with a high Z scatter that can do proximity as I showed, and it can do also Compton imaging. And if you want more details, there is a complete simulation analysis published here. So just let me conclude, collimatorless modalities could open a window for quantitative preclinical in vivo studies of actinium-225, and we could measure sub-macrocuris activity of actinium-225 daughters in a mouse phantom with a collimatorless detector. Collimatorless approaches present an opportunity indeed to perform quantitative longitudinal studies of actinium-225 daughters for the first time. And I would like to thank my group, my collaborators, and the funding sources. Also, we have some funding for this analysis, so please, if you're interested in joining the effort, contact me or contact Yahoo. And just a last advertisement, if you're interested in actinium-225 imaging, we have a very nice presentation on Saturday by Robin Peter on the microscale dosimetry of this isotope. And with that, I'll...
Any questions?
Thank you. I have two, if I may. One concerning this actinium decay to the daughter nucleus, which then has a lifetime of about 5 minutes. So I find it very interesting hypothesis or question which you ask. So what is the conclusion? Does it stick to the ligand, or it's still unknown from
this study? I cannot tell you yet. From other studies, I don't have references in my hand, but I've seen that there are some claims of that, but I cannot give you a number or.
Thank you. But it was very interesting to see the daughter nucleus as a separate images. And I have another question concerning the last principle or last concept for combining the two methods, Compton and proximity. You told that the first layer will be high Z, but the higher is the atomic number, the less is the Compton contribution. So there is some optimum probably. Yeah.
That's right. It's an optimization problem. You also have that high Z has higher density. So in absolute terms, you also have more interactions there. So it's an optimization problem, and it's all on the paper. We optimize it to 6 millimeters thickness is the optimal thickness.
So my question, I don't know if that last slide that you showed will answer some of it, but I thought, like, my understanding is one of the issues with the alpha emitters is like microdosimetry, that you could get little areas of concentration, then it could do a lot of damage to tissues. So is there a way to get to that level? Because it seems like right now you're kind of at an organ level versus more granular than that.
Right. So currently, I should say that in vivo is impossible to see. It's really hard, I would say, to see actinium, right? So I think it's going to be a long time till we actually go to microdosimetry in vivo. So here we are advocating for longitudinal analysis, organ specific. For microdosimetry, we talk about microdosimetry is literally at the micron level, right? Not even technetium SPECT or PET can achieve that, right? So I think it's going to be very challenging in vivo.
Okay, and there is a last one in the chat, which I don't totally understand. Does ex vivo analysis work instead, or do you have any plan of comparison?
So the state of the art currently is to perform ex vivo analysis, so that you basically dissect the mouse and you put each individual organ in a gamma counter. We are planning, once that we have the in vivo analysis complete, we plan to dissect that mouse and cross-check that our prediction is actually true.
Okay, thank you very much. And with that, we complete the